Okay. So we did this basically, this preparation of ether from alcohol, and we also did the mechanism of this. Okay.
Yes, sir.
And there was a question. Did you do it?
Sir, I got disconnected, sir, after the last part.
Okay, okay. Yeah, yeah. Got it. Yeah, got it, got it. So can you do this question now?
Yes, sir, I'll try, sir.
Okay, just give a try.
Yeah,
Then today we are gonna end this chapter, complete this chapter, and we will do after this chapter we will do some questions. Basically, a lot of question on this chapter, and in next class we are going to start electrochemistry. Okay.
Okay.
Okay, just give it a try and then I'll start. So this is called concentrated HCl and reagent Cl2 Lucas reagent. You just need to replace this OH with Cl. I gave this first.
Yes, sir. Okay. Yes.
And you will get H2 as byproduct. Okay. So can you name this compound, please?
Yes, sir.
Yeah.
Sir, is it wait? Is it two chloropropane?
Is it 2-chloropropane?
Yeah, 2-chloropropane, right?
No, it's not right. Can you tell me what does this prop means? How many carbon?
3.
3 carbon. How many carbons in the parent
chain? Oh,
chain?
it's 4. Bute. Yeah, sorry.
Total carbon in the compound, can you count it? Total carbon in the compound.
Total carbons in the compound. 6.
6. How can you say that it is 6 carbon in the compound? Look at the compound carefully and let just count the number of carbon atom.
It is 4, sir. Total carbons, right?
Total carbon is 4 only.
Yeah. Okay, 4.
1, 2,
3, 4. Yeah, 5. I counted that also. The other part.
5 carbons are there, not 4 and 6.
So it's pent.
1, 2, 3, 4, 5 total carbon in the compound.
Yeah, so pentane.
Not pentane. This you are going to number it like this. So in parent chain, you have 4 carbons and 1 as a substituent. So the name will be 2-chloro, 2-methyl. 2-methyl
pentane.
Not pentane. How many carbon in the parent chain? Bute, 4 carbon and singly 4. Bonded. So butane.
Yeah. Okay.
Now see, the second method of preparation is called basically Williamson synthesis. Williamson synthesis. So see, what is Williamson synthesis? Williamson synthesis is also known as name reaction. So basically it is a laboratory method for the preparation of symmetrical and asymmetrical ether. So what is symmetrical ether? It is CH3OCH3. This is symmetrical. Both sides same alkyl group. And what is asymmetrical? Both sides different alkyl group. Are you getting my point?
Yes, sir.
So this is asymmetrical and this is symmetrical. Yes or no?
Yes, sir.
So see, this is Williamson synthesis. So it is laboratory method for preparation of symmetrical and asymmetrical ethers. So basically how we are going to prepare, it's very important. Basically we are going to introduce alkyl halide and react this with alkoxide. What is alkoxide? So this is alkoxide. So what will form here is very important. RO, R dash. I'm going to take this as R dash, RO R dash, and along with the byproduct that is salt NaOH. So what we just did here is very important. An alkyl halide of, oh wait a minute, an alkyl halide is allowed to react with, or an alkyl halide react with sodium alkoxide. Sodium alkoxide, and you will get your product. Please write it. Let me know when you are done with this. Are you done with this?
Yes, sir.
No, very good. Now see, secondary and tertiary. If you have, wait a minute, it's not working. Yes. CH3, CO, Na, and CH3. And you are going to react this with a primary halide, that is CH3Br. Then what happens? You just need to replace this Na with this CH3 and you will get your ether. NaBr will be eliminated like this. So one of the most important point is that, wait a minute. One of the most important point is that better results or better products, better results obtained if the alkyl halide is primary. If alkyl halide is primary. Whenever alkyl halide is primary, the better results will come. But if you are going to use secondary or tertiary alkyl halide, in case of secondary and tertiary, in case of secondary and tertiary alkyl halides, elimination will take place. Elimination. Can you hold a minute because it's hanging? Are you there?
Yes, sir. Yes,
Are
sir.
you
Yes,
there?
sir. Yes, sir. I'm there.
It was hanging, that's why I just stopped the sharing. So now can you see the screen?
Yes, sir. I can see it.
So see, elimination competes over substitution. Elimination competes over substitution. So you can see easily that whenever there is primary alkyl halide, you can recognize whether it is primary or not. Tell me.
Yes, sir.
You can recognize whether it is primary halide,
Yeah,
secondary
yeah,
halide,
yeah.
or tertiary.
Yes, yes, sir. By looking at it.
Now, the point is that CH3, CBr, CH3, CH3. This is tertiary,
Yes, sir.
and you are going to use.
NaOCH3.
You can see this is alkoxide. So one of the most important point is that if this is tertiary or secondary, then elimination will take place. Elimination will take place, and what will happen here? CH3 C double bond CH2, CH3 C double bond CH2, and there is CH3, and along with NaBr, there will be another product that is CH3O. So whenever there will be tertiary or secondary halide, then elimination will take place and alkene will be the alkene will form. Alkene will form. Are you getting my point?
Yes, sir.
Please write it.
So I can just scroll up.
Yes. I think you are done with the okay. Please write it.
Yeah.
Let me know when you are done with this.
So can you scroll down?
Yes.
Done, sir.
Very good. Now see, phenols can also be converted to ether. So I'm going to write about it. Phenols are also converted to ethers by this method. So basically you can see, if you have a phenol and you are going to react this phenol with NaOH, sodium hydroxide alkaline, so there will be a product phenoxide O minus Na plus, and then again you are going to react this with RH. So what happened here? This X will take electron from R, and in order to stabilize this R, this oxygen will attack this. So what will happen here? You can see there will be a bond between O and R now, and a byproduct, that is NaX. This is how phenol converted into ether. So please write it. Let me know when you are done with this. Are you done with this?
Yes, sir.
Very good. So this is there are two methods of preparation of ether. So we just completed the second method. Now we are going to study about the chemical reactions. or you can say chemical properties of ethers. So chemical reaction, the first subtopic of this is cleavage of CO bond in ethers. Cleavage of CO bonds in ethers. So now you can see, basically ether are least reactive functional groups. So we can write a point. Ethers are least reactive of the functional group group. So if it is least reactive, that means it is more stable. Yes or no? Harsh.
So can you repeat the question, sir? I'm kind
Yes.
of lacking.
If it is least reactive, that means it is very
More
stable.
stable. Yeah.
More stable. That
Yes.
means if you want to break this CO bond, there will be drastic condition. So the cleavage of hydrogen. So wait a minute. The cleavage of CO bond. The cleavage of CO bond in ethers takes place under drastic conditions. Under drastic condition. Why it is so? Because it is very stable. With excess of hydrogen halides. With excess of hydrogen halides. So we can see if you are going to react this ether with alkyl halide, you need to take alkyl halide in excess. So first it will form Rx and ROH. First it will form Rx and ROH, and then again this ROH will react with HX since HX was in excess. So now it will form Rx plus H2. Are you getting my point?
Yes, sir.
This HX is in excess. That means basically it will react to form alkyl halide. Then again you are going to react this alcohol with HX because HX is present in excess. That's why.
Yes. Okay.
So please write this.
Sir, how many more topics are left, sir?
How many?
More topics are left in this chapter.
Oh, basically chemical reaction, cleavage of CO bond.
Okay.
And after that, electrophilic substitution reaction.
Okay, sir.
Are you done with this?
So just a minute.
Okay, take your time, no problem.
Done, sir.
Okay, very good. So this was the cleavage of CO in normal ether. Now in aryl ethers, we are going to see. So aryl ether, that means benzene. Aryl ethers are cleaved at the alkyl oxygen bond. Oxygen bond due to the more stable aryl oxygen bond, because there will be resonance. That's why it is more stable. The reaction yields, or the reaction produce, you can write phenols, phenol and alkyl halide. So now you can see this is aryl ether. So if you are going to react this HH, there will be formation of phenol OH, and this RH will be eliminated. Please write. Are you done with this?
So just a done, sir.
Very good. Now see, if there are two different alkyl groups, ethers with two different alkyl groups are also cleaved in the same manner. Like if you have ROR dash, ROR dash, and you are going to react this with HX. So it will be RX plus R dash OH. And also the order of reactivity, which is very important and can be asked directly. The order of reactivity of hydrogen halides is as follows. So basically, iodine is the best cleaving group. That's why it will be HI, HBr, HCl. And also, since ether is very stable, the cleavage will only take place. The cleavage of ethers takes place with concentrated HI or HBr at high temperature because it is already stable. So in order to make a new bond, we have to break the old bond, which is very stable. Are you done with this?
So just a minute, sir. Yeah. Done, sir.
Very good. See, if you are going to have different alkyl groups, then when one of alkyl group is tertiary, when one of alkyl group is tertiary group, then the halide formed is a tertiary halide. When the halide formed is a tertiary halide. Like if you have this compound, so you can see one is tertiary and one is only CH3 superprimary. And if you are going to react this with HI, then alcohol will form with this CH3OH and the halide will be formed CH3C and I. Tertiary halide will be formed. Because there will be the formation of carbocation. I will explain the mechanism. First, write this.
Yes, sir. Done, sir.
Very good. So if we are going for mechanism, you can see CH3, CH3, and then CH3, and then this O, CH3, and we are reacting this with HI. So this, as we know that oxygen has lone pair electron rich species, so hydrogen will come here, and there will be positive charge. There will be bond between oxygen and hydrogen, and this is a step one, which is slowest step, and then in order to stabilize itself, oxygen will take electron from carbon, and now there will be carbocation formation. And this CH3, oxygen will go with this CH3 and hydrogen, and it will be CH3OH. Now, since this carbocation is left only, so this carbocation will react with this I minus from HI, and now it will form CH3CI, CH3. Please write.
Yes, sir.
Let me know when you are done with this.
Yes. Done, sir.
Done. Now I'm going to give you a question on this.
Okay.
So the question is basically CH3, CH2, again CH2, and then O, and then CH3, CH3, CH2, CH3, reacting with hydrogen iodide.
Okay, sir. Just a minute.
Yes. Can you do this?
Yes, sir. Yes, sir. Just a minute, sir. I'm doing it. Done, sir. So I can just see if it's correct. I can solve it. I'll see if it's correct.
Yes, you can see since we are reacting with this HI.
Yeah.
So tertiary will go with halide. So the product will be, you can see CH3, CH2, C, and then I, and then CH3. And with another alkyl group, there will be formation of alcohol.
Yes, sir.
That means propanol.
Yes, sir. Yes, sir.
Got the same answer?
Yes, sir.
Now we are going to start electrophilic substitution reaction. So this is our electrophilic substitution. So you can see this is electrophilic substitution. Before going to start this, can you write the resonating structure of this? Can you write the resonating structure of this?
Yes, sir. I'll write it.
Are you done with this?
So just on. And the last part. Done, sir.
So you can see
Yeah.
moving this pi electrons here we have to move this to here, as carbon makes only 4 bonds. So there will be
Yes, sir.
negative charge, and now there will be double bond.
Double bond OR.
This is OR,
Yes,
and
sir.
this is positive.
Yes, sir.
Again, if you are going to see, if you want to move this pi electron to here, you have to move this to here. And again, this will be, and this will have
Minus.
negative charge.
Double bond
And
OR.
again, this OR positive.
Yes, sir.
As it is. Now again, this and this. So you will have negative charge here, and double bond here, and double bond OR positive.
Yes, sir.
Again, in order to make move here, it will have to move there. So we just delocalize the pi bond,
Yes, sir.
and here it will be O. Yes or no?
Yes, sir.
So this is the resonating structure of electrophilic, ether.
Ether.
Okay. In this aryl ether, we can say electrophilic substitution reaction, we are going to start halogenous. What it is? Halogenous. So basically, we are going to take an ether, aryl ether. This is O, and this is basically methoxybenzene basically, and its common name is very important, that is, and famous, anisole. So in order to react this anisole and to do halogenation, we have to react this with Br2 in presence of ethanoic acid. In presence of
Ethanoic acid.
ethanoic acid. So what happens? Br will be added at ortho and para position, and you know which one is major?
Yes, sir. Para, sir.
Which para? This is para, this is major, and
Yes, sir.
basically this is minor. Ortho will be minor. OCS. Now the important point is that you can see its name will be P bromo anisole. Para bromo
Anisole.
anisole. This is major, and
Yes,
this
sir.
is ortho
O
bromo
bromo. Anisole.
anisole. This is minor. So please write.
Yes, sir. Done, sir.
Very good. Now, after halogenation, we are going to take another electrophilic substitution reaction, that is
Friedel-Crafts reaction.
Yes, we already know that this is of two types, alkylation
Yes,
and
sir.
acylation.
Acylation.
This is Friedel-Crafts
At
reaction.
ortho and para positions.
Yes. So we are again going to take this anisole. This is our anisole, OCH3, and we are going to react this with CH3Cl in the presence of anhydride AlCl3 in presence of carbon disulfide. So this CH3 will be added at ortho and again at para. So you know the major product.
Yes, sir.
So para will be major and ortho will be minor.
Yes, sir. Minor.
So this will have a name, 2-methoxy toluene. 2-methoxy
Bromine.
toluene. This will be minor, and this will have a name, 4-methoxy. So this will be major. So you can also call it Friedel Craft. Alkylis. Let me know when you are done with this. Are you done with this? Yes. Are you done with this?
Oh, yes, sir. Yes. Sorry, sir. I got disconnected.
Yeah.
Sir,
Now you. Yes.
sir. Actually, I just had a request. So can you just finish up the class early, sir? Because I'm not feeling well today.
Okay. No problem. Can we just go for 5 to 10 minutes?
Yes, sir. Yes, of course.
In order to do that, we are going to complete this chapter. That's why.
Yes, sir. Sorry, sir, because I'm not
No
really feeling
problem.
well today.
Anhydride AlCl3. So what happens here? There will be addition of. Just write with me.
Yes, sir.
There will be addition of COCH2 and COCH at ortho and para position. So you can see this will have a name 2-methoxy acetophenol,
Acetophenol.
and this will have a name you can
4-methoxy.
write 4-methoxy. This is major and this is minor.
Yes, sir.
So this is it for today. Are you well?
Sir, there is one more, right? Nitration. I guess.
Yes. Are you done with this?
Sir, just a minute. I'm on the
Second part, right?
reaction, sir. Yes, sir.
So there is the next reaction is nitrogen.
Done, sir.
Very good. In nitration, we need to add nitro group.
Yes, sir.
So this is OCH3. So there will be sulfuric acid H2SO4 in the presence of HNO3. So we have new OCH3. And again, so its name will be again the same, 2-nitroanisole,
Yes, sir.
and its name will be 4-nitroanisole. This is our major product, and this is
Yes,
our
sir. Minor.
minor product. There will be a steric hindrance, that's why it is less stable minor.
Done, sir.
Okay, so this is it for today. I'll see you in
Sir,